Hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. I'm very allergied, as you can see. But we have some relatively straightforward stuff to do today, so hopefully it won't be a problem. We can basically just start where we left off yesterday and try to make our lighting system use pre-computed templates for figuring out what we want to do with our raycasting from any individual raycast sample point. And also, raycasting seems to be in the news a bit lately. I don't know if you saw. But there's a lot of talk about pushing future GPU development directions towards a ray tracing future, which, as I sort of mentioned yesterday, I think in the pre-stream, I am very much in favor of. I like ray tracing. I don't have strong opinions about whether ray tracing or rasterization is the correct way to do things or anything like that. I just like ray tracing better. It feels cleaner to me and easier to experiment with. And I've never really liked the sort of large number of stages you go through when you try to make a rasterizer to try and approximate lighting. So I'm pretty happy about the fact that people are trying to start a push towards the ray tracing world. I don't know if we're going to get there, but, I want us to get there, I guess is what I'd say. So, it's kind of exciting to see people giving it a shot. And I think it's a good direction for GPU vendors because at the end of the day, ray tracing parallelizes pretty darn well. And so, they're not really in a position to be able to up their clock rates much, right? And so serialized rasterization kinds of stuff with lots of pre-doing lighting and then you have to wait for the next stage to do something and that sort of stuff. I feel like just, hey, stamping down gigantic sets of ray tracing cores may not be a bad idea hardware-wise. Maybe we're at that point where that's really what we should be doing. I don't know. Totally outside of my area of expertise, I have no idea, but point being, I'm kind of happy that people are looking into that, and maybe we'll see some fruits of that down the line. For now, I'm just happy that we have our own ray tracer for doing our lighting, and I want to make it a little bit better, so that's exactly what we're doing today, is trying to come up with some better sampling schemes. We've been playing around with it for a week or two. How we want to cast rays out of a point, part of the problem. And that's what I'd like to start looking at today. So, a couple things we don't know at the moment. And we got to look at them all today. So first of all, just at the end of last stream, I changed to using a template for doing our sampling. And it looks like it kind of broke things a little bit. So I think we've got either some errors or, we don't really know. I don't know exactly what's going on. All I know is I don't think we have a completely clean result here with that switchover. Now it could be that we've implemented it just fine and our pattern is bad because we haven't actually put in a real pattern yet. And maybe the fact that we did a randomized pattern, maybe this isn't enough randomized patterns to actually even out the light, or who knows. But it doesn't look the same as it looked before when we move around. And it should look roughly the same. So we don't really know exactly what's going on there. So we basically have a couple things that we want to accomplish going forwards. Number one is we want to go ahead and put some real patterns in. Number two is we want to introduce some debugging so that we can verify that these patterns are being applied the way we think they are. Because obviously there's plenty of things that can go wrong as part of this process. And we don't know until we inspect a little bit more cleanly and figure that out. Now, for example, you can see right here, why is this not getting very much light, right? It just looks wrong. And so I'm guessing that we've got some problems, and we're going to want to look at those problems in more detail. So that's our job for today, to start looking at that stuff. And there we go. So for starters, the first thing that I want to do is I want to just go ahead and enable our debug line support again, because that will allow me to draw where we're sampling. And then what I'd like to do is just take a look at how those samples are working out so that we can, get some opinion of what's going on. Now, if you remember how this used to work, and you can see that this, well, you know what, this is something we can switch back on, actually, for those of you who maybe missed last stream. So you can kind of see here, here's what the lighting looks like when we were generating the random samples using the previous method, which generates them in line. So just at the time that we want to generate the random samples, we generate them. And you can see that the lighting looks pretty reasonable, like it's a pretty reasonable approximation of the lighting to the scene, it seems like, to me. You know, that's just my sort of like gut take on it, is that this you know, isn't so bad. And we haven't run any really rigorous testing on it or anything, but it seems reasonable. And then when we go in, if we actually switch that if 0, you can sort of see how the lighting changes there, and it's not obviously super wrong, but it does look, you know, it definitely just looks more incorrect than the version that was generating the randoms on the fly. And that's just why I say I think we've got some bugs in there, or at least if there aren't bugs, we've got a problem with the way the random pattern was working. And it's yeah, again, it's less about knowing if it's a bug or not, it's just noticing that suspicious behavior, and that just reinforces the fact to me that I want to see this. I want to be able to visualize what's going on so that I can know what I'm looking at, what is causing that particular effect to occur, because I don't trust that it's reasonable. It could turn out to be totally reasonable. It could turn out to just be a straight up bug, and we need to know which is which, right? Okay, so I want to re-enable this sort of situation. And what this is the thing that lets us draw our debug lines, right? And the problem is we kind of updated this code since we were drawing these debug lines. So I need to extract the debug lines in a more straightforward way. Now hitbox at the moment is the only thing here that it's complaining about first. And then it's got T-ray is another one, right? So we've got a couple of these things that we want to be able to access sort of individually, and we need to figure out how to do that. So let's take a look at how we're going to go about doing that. So if I come back here and look at how we made our stuff for 4 wide, you can see that we still have a T-ray, it's just 4 wide. So what we should be able to do is access T-ray by just extracting it from the raycasting result and pulling out the subrayth one of those. So that's not a particularly hard one to get. Hitbox is really just the thing that was telling us whether or not this particular thing had a hit. And so again, that one is really just this. So we can just do that, where we look to see whether or not this thing got hit or not. And then that replaces what we were doing here. Then finally, the last thing, if you notice from the compiler, is we just don't know what direction this thing goes in. But we can know that, obviously, right? We can know what direction it goes in because we made a bundle of 4 directions that the thing goes in. So this is really just a case of pulling out whichever one of those we're on. So we can just say, hey, why don't you give us out of the bundle of 4 that we made, we have a thing already that extracts those when we find that we actually need them, which is this get component call here. And so that'll pull out the sample D. So at that point, then we are actually doing those debug lines. Those will now get updated, which allows me to see exactly what I want to see, which is where the samples are happening. We also have the ability to set this debug point index. And so the interesting thing about the debug point index, if you remember, we have this thing that sort of says, hey, where do I want to pick? Who do I want to pick for grabbing those debug? It basically allows us to pick a point in the world and say, show us the debug cast from this location. So we can actually move it around and look at some different stuff, right? So here is the version of this that's working. I believe this is the debug lines that happen. I'm gonna move the light out of the way. These are the debug lines that happen. I believe when we're when we're using the correct lighting. I think, right? Yes. So this is using the lighting, and correct is a strong word here. This is using the lighting that we thought looked, or I thought looked more reasonable, right? And you can kind of see what lines we're shooting out there. So now I'm just going to go ahead and look at what happens if I shoot out the template lines, and we can see what those are. Okay, so you can see those are totally borked, right? They're just not rotating. I should see it rotating through a whole set of them, but it's not. So like I suspected, we're just picking slightly wrong here. Totally fine. We threw that in at the end of last scene. I'm not upset about it at all, but it's just that's exactly what I wanted to know. And so we need to take a look at it. Now, the other thing I don't know is those red lines there, those are ones that didn't hit anything, I believe. I think that's okay, because if I look at where those red lines are pointing, they shouldn't probably have hit anything. It looks like they managed to escape out the side and out the top. So I don't think there's any cause for concern there. And all these rest of these lines are correctly green terminated. And you can see they're terminating at the places where they would have hit. Now remember, it's a little bit confusing because we allow early termination if you hit a bounding volume early and then you gather the light that's aggregated from that bounding volume. That's by design. So again, nothing particularly weird here other than the twitchy, like this should be changing every frame and it's not. So we just need to go through and like start cleaning that up and this should be fine. Okay, so that would probably explain what's happening with the lighting. If you look what's happening with the lighting now, the reason why it's only slightly, slightly wrong, or I don't know how you want to say it, is because it's using sort of just two patterns to sample the light, so it's getting kind of a weird result. And I think we can immediately sort of figure out why that is. The reason for that is we haven't really done much to permute the light. I was just using the sample point index, and so if the sample point indices come in relatively stable, meaning we don't really shuffle where entities are very much per frame, then that's just not going to add very much randomness. So what I think we need to do here probably is just add an offset here, something like this, where we take a certain amount of sample point entropy and we add that in, and that comes from the series itself. So I can just say sample point entropy equals, random U32, and that would give me, I don't actually know what we called this. Let's go ahead and fix that, shall we? No sense typing more than we need to. All right. And so now that we've got a little bit of entropy in there, I'm expecting to see more variation, and I do, right? Now, it's not going to be as much variation as before because, again, we are not actually giving it in full randomness. We're just giving it 16 different random samples to go through. Now, that 16 is fairly arbitrary. We can make as many as we want, but that's the idea here, is that randomness is sort of coming from a set of patterns that we're permuting through. And what we can see now that we've fixed that is we're much closer to the original pure random version, which is what I wanted to see. So I'm much happier about that now than the previous version, which was kind of wrong. So what I'd like to do now is actually replace those lighting samples because the whole point of this was to start using better sampling patterns. So what I'd like to do is replace those sampling patterns now with one of the patterns that we were using before. And we can try some different ones. We don't need to do anything in specific. We can try a couple different ones. But what I'd like to do is basically give us the ability to kind of cycle through them a little bit so we can play with that. So we know that we've got these generate samples situations here, right? What I'm going to do is I'm kind of going to make this into a thing that is, probably a little more general than we need. But I'm just going to say, okay, look, let's go ahead and pull this out. I'm going to put this all the way at the top. And I'm basically going to make a little system for doing these samples, right? And what I want to do is I want to make a template, right? I want to say, okay, this is a lighting sample pattern or something, right? And these lighting sample patterns, I'm just going to say, whatever, give me the name of the function. And what I'm going to do is I'm going to make that pattern be the template that we've defined already that all these things use. So this gives me a way to like define one of these, right? once I have one of those, I'm going to use the macro here to define the callback. I don't really want that in there probably, so I can use it for other things later. But anyway, I'm going to use it to define the pointer, like a callback to this thing, so I can use a pointer to refer to one of these. And so I'm going to say there's a lighting sample pattern, I don't know, generator. How about this? Seem good? There. I'm going to use that to generate a pointer here basically for that, so that we have a type def. It's not a pointer, but it's a type of this thing, so that I can use it to declare pointers to it. And then I'm just going to make all of these people use that. So here's the polar samples, right? Here's the spiral samples. Here's the Poisson samples. And now each of these is like definitely uniform because we're using a macro to generate all of them, right? So then what I'm going to do is I'm going to loft this up and put that into the main body of the lighting system here. And so inside the lighting solution, I can now say, okay, which pattern generator or whatever are we using? I can do that, or I can do, whatever I want there, right? In fact, well, you know what? Now that I think about it, I don't even really need to do that. I can just put it here, and that'll be fine with me. So what I'm going to do is say that we have a certain number of lighting pattern generators, right? And I can put that right here. And then I can just put the names of these things into an array so that I have, I'm just, creating a way that I can refer to these things generically, so I don't really have to care which one I'm using, right? So now I know that I've got this many lighting pattern generators, and if I wanted to, right, I could cycle through them. So I could do something like lighting pattern generator index or something like that. And then what I could do is say, okay, let's just make a function that that does whatever it needs to do to initialize the lighting with a particular one of these. All right. So in order to do that, let's say generate lighting pattern, and I'm going to use the lighting solution. And I guess all I really need to do here is say, well, trying to think of how I want to structure this. But let's say I do generate lighting pattern, and I've got this solution here. And what I want to do, the way that I'm kind of thinking about this is, I feel like if I set maybe a debug value, I feel like I could even extend this a little bit more and just say like lighting pattern is a thing that has a name and a lighting pattern generator. I don't know why I didn't actually put a type in here. Sorry about that. I'm going to make a name here, and then I'm going to have a generator pointer, right? And what I could do is I can then just say like, okay, maybe I just have a thing here that's like, you pass the function, and it just automatically generates, the name of the function and the function, right? So this basically gives us a table with names in it so that we can print out which one we're using if we want to. And so when we receive pattern index here, what I could do is just say, in fact, I could even just get rid of this entirely. Just say generate lighting pattern. And then what I do is I say, okay, I need to generate a certain number of these, right? So I need to take the random series from the solution. And then I need to go through however many of the sample patterns I need to generate. So this is like, I don't know what I want to call this. They're kind of like different versions of it. So this is like a version index, because we're going to generate many different versions of the same pattern, right? And I want to go through however many there are in the sample point array. And then I want to, oops. I should probably change the name of this from sample point to something else. It's really sample direction, but we'll do that in a second. So what I want to do here is just say, okay, let's call whichever one of these we're actually using. And in order to do that, I can pull one out here, right? So I can say lighting pattern equals lighting pattern generators, pattern index, and we'll just let it wrap. So however many there are in this thing. Right? So this gives us the ability to just kind of loop through these. And then what I want to do is I want to call the pattern generator with the information we had before that it needed, right? One was the series to use, and I think, yeah, these series is just kind of, so I feel like these series should just get used actually. I don't think we need to do this thing at all, actually. So we can just kind of get rid of this entirely here and just use the random set that we're passed in, which seems more sane to me. Just fix that, because these are offline now. We didn't know if these were getting done in real time or anything like that. We know they're not going to be now, so they can be kind of as slow and pokey as they want to be. Okay. So now we can go through each of these and say, okay, put it in the sample point array that corresponds to whatever one of these we're trying to generate here, and off you go, right? Now, it's a little bit squirrely because we know we want to generate v3-4x versions of this stuff. And so one of the problems that we're going to have is, yeah, these are not generating things v3-4x. Now, maybe we don't want to generate v3-4x because it's just a pain in the butt to do it that way since it's more this weird packed format. So what I could do instead, too, is I could do the packing, right? So what I could do is say, all right, let's suppose we've got 4 of these arrays, right? And I could just have it generate them and then do the pack myself. So for example, we could do a temp array here that had, you know, a array of 16 of these that was 4 times, right? And when we pass this in, we can literally just call this thing 4 times, right? That allows these to work on arrays of v3s, which are, you know, more straightforward, don't involve any SIMD or anything like that. They can just do their generation the old-fashioned way. And then when I actually go to use it, I can say, okay, let's integrate them back to put it into the array proper. So when we go to put it in here, I can say, you know, loop through this array. And in fact, I could just pull this out. Like so. So I can grab out our destination here, and I can say, like, okay, you know, however many of these we're going to do. We need to make one of these v3-4x's. Oops. Of course, I don't remember how to do that. Is it just like that? I think it might just be like that. And we're going to make that out of the various sliced elements of the randomly generated set of patterns, right? So we know that if we're generating these, well, you know what? and there's even another reason to do this, because I was forgetting one step of the process, but there's another reason we want to do this too. And that is actually because when we generate these things, we're actually generating 64 of these, right? Now that I think about it, it's actually a little more complicated than that. We're actually generating 64 of these, and then we need to group them, right, into bundles that cast together. So actually, I didn't need to do quite that. We actually want to do this, and then we need to run a thing here that will cluster, right, that will go grab. So there's actually another part of the process that has to happen here. So it's actually even more complicated than that, right? So that's good to know. So anyway, but we can still do a temporary version of this that will just run slowly. Because remember, our routine will still work. It'll just run more slowly if we don't bundle arrays that are close to the same direction. So to start with, just to get things working, we can just stuff any 4 arrays in there. So we can do something like say, okay, we've got 4 times dir index plus 0, 1, 2, and 3, right? So we can just say like, all right, here is what we're going to pack in there. We're just going to grab any 4 of these, and it's fine, and off we go, right? So that would do it. And the problem, again, with this is just that it won't have any particular coherent... the 4 arrays per bundle will just be pointing in any random direction. So we will get poor performance out of this compared to what we would hope to, or at least we think we would, right? So that's an easy way for us to generate the lighting pattern. And hold on a second, let me debug all this. That's not supposed to be there. And this should be a plus. And then we're good. So that's pretty much everything there. Now what we want to do is actually call this thing. So inside the init function, which is right here, where we're doing this random generation, we can put the random generation into its own system here, because I don't think we have one of those. We've got polar samples, spiral samples, and Poisson samples. We should just add another one here, which is like generate white noise samples or something, right? And this would just do the straightforward version of this. So this would generate pure white noise. So and one of the things about this is we've hard-coded it to 64. The reason for that is because I don't want to force these things to be parameterized on a number, because, like, for example, here we were fine-tuning it very specifically. So that's why you'll notice I'm just kind of hard-coding 64 in here. I wouldn't be adverse to making it parameterized on the number. I just don't want to do that yet, because it just creates more work for trying to, like, now you got to make a thing that generates this table correctly for any number, right, and whatever. So I don't know. Some things are much easier to parameterize that way than others, and so for now, we're just going to stick with, they only generate 64. In the future, if we're feeling saucy, maybe we would do something different, but not right now. Okay, so if we generate random bilaterals here on the white noise one, this we've decided is kind of not a particularly great way to generate these necessarily, but whatever. And so here I'm going to generate a random unilateral pointing upwards. This is not really white noise, it's kind of biased. So we can improve that as well if we want to. And this can just get actually assigned directly as well. So that'll generate random samples for us. And that gives us a pattern here as well. Now in here, when I do the generate lightning pattern, I'm just wondering if I can do this. I don't really remember to what extent we can display string values or anything like that. It would be nice if we could, but I don't really remember. So yeah, we don't really have a string-based thing here that I can see. We almost want like a debug note, right? Where we can just say, hey, this thing wants to have an actual, just a value, like a char star that you print. You know what I mean? But I don't think we have anything like that. That I know of anyway. Pretty sure we don't have it. Yeah, I mean, Yeah, I don't think we have anything like that. Because the way that we store these things internally, right? Like, the way that we store these things internally, they've got... I mean, they have a fair bit of stuff stored with them here, but it's not really... It's not really the same sort of thing, although the name... So the name and the GUID can be specified separately, so I suppose that would probably do it, right? I'm going to take a look at how this is parsed here. These are all just drawing commands. So here, when we do data, I think it's right here. This is where we do store event. And you can kind of see when we come through here, the event, I guess, just gets... I want this kind of over on the other side so I can see it better. There we go. My head was in the way. When we get one of these events, that's what does the cloning, right? So if we wanted to, we could, I guess, do something here that would potentially... Yeah, I mean, there's a lot of ways we could handle this. Here's how I think we should handle it, because it does seem like at this point we probably want to keep the old DLLs around, since we'd had problems with that, and it took us too much work to really make it so that we could unload old DLLs. It just seems like a bad idea, right? It seemed like what we would want to do here is just make one of these types be a pointer to a string. Because we want to be able to just do something like, you know, something like that. You know what I'm saying? Where we can just make a char star and have that work. And then in here, there's just a like, okay, you know, and that's probably more like up here with the basic types, right? Something like this. And then if we want to, we can look at like, you know, where this stuff gets printed out. And you can kind of see we don't really want any interactions with them or toggles, really. So the only place we really care would be here. And so what we could do is just say like, okay, there's a string pointer case here. We don't care about this. So when we go to print it out, it's just like, yeah, you know, print it out. Just print it out. And so in theory, that would let us do printouts of that form. Oops, sorry. And here I could just say, yeah, let's just say that we're going to store one of these things. So we want to do a debug value. And I'm going to call it, let's see, pattern name, right? All right. So now, if I go into the interface, I'm hoping that it's just as simple as saying, all right, let's just make one of these debug value calls that happens to work with the with a string, right? And if we take a look at what's going on here, I think we should be able to, I guess, like, you know, maybe I want to do this just so I can make sure that I have kind of my own version of it that I know I'm calling specifically. But I think that should be about it. So that will become a, that will all become very straightforward. I don't know why debug type unknown gets passed to record debug event there and gets set after the fact, but I'll continue that pattern. And then when we go to set the value, I think we just need to do that. To be honest, though, I don't know why we even need to do this. We're not allowing this to be edited. So really, I can just do that. So honestly, I don't even think most of that's necessary. I don't even know that we need to call that. I think we can just do that, right? Because all those gyrations were to make it so that we could get around the, you know, C's sort of unwillingness to play with us and to avoid using some nasty template ugliness. But I think that's really all we need. So in theory, I think now inside our lighting stuff, if we wanted to call our init lighting code, if our lighting code wanted to just call lighting pattern generator, I think it can. So in order to do that, we would just say, here's the solution, and here's the lighting index we want you to use. In theory, it will generate using whatever that pattern generator is, and we should also see a thing in here that says which one was used, if I'm not wrong about that. Although I don't know, since we don't call it multiple times. I suspect that's it right there, and so it looks like I wasn't quite right about it. Because you can see that it doesn't actually show anything, right? This thing was supposed to, that thing was supposed to be it. So, okay, not quite correct. But let's take a look at that, because I would like that to work. So we do need to do these two things record the event, and that seems like it should be okay, right? It's the same as if it was a B32. Let me just take a look at what value set event data is supposed to do. It sets the type, which we do, and it sets the value, which we also do. So it seems like that should be okay, and I'm not quite sure why it wouldn't be. Let me check that out, though. That's in init lighting. So if I, oops. Ah, yes, I forgot. Since we're not currently compiling with the C runtime library in our Win32, we are missing our seal and floor functions, which we hadn't done yet. And I'm not sure why I can't get it in D mode to inline those. Because I want it to inline those, but it doesn't seem to want to. And so I'm wondering how I would do that, right? Force inline seal F MSDC. Because I want it to inline these. And I'm not sure exactly how to make it do that. I wonder if I have to specify like an Arch SSE2 kind of thing or something like this to get it to do that. That's not relevant. Like, I just want to say, yeah, you know, anything you were going to inline, I want it inline from the CRT. I don't want you to optimize my code anymore, but that should get, and maybe there's just no way to do that, right? Like, maybe it's going to do that one way or the other. Which I guess is fine, but, you know, implementing seal or floor is actually pretty straightforward. We can throw that in there, I suppose, with the other thing we can do. So, the trivial way to implement seal or floor is if you don't care about which version of SSE you're using, you can do that. So I can show you there's some pretty simple stuff in here for that. Let me just... so we want, let's see. I want my rounding functions. Where are you? So the ceiling and floor functions are special cases of, here it is. This is the one I was looking for. So by the time you get to SSE 4.1, which we have not been using yet, so I don't know that we really want to leave this in, but for now it's a pretty trivial way to do it. And to be honest, we did look before, and it was not very similar to when we looked at the start of this project, because obviously we've been programming on this for a while due to the slow pace of the 1 hour, or well, I should say 4 hours a week, 4 to 5 hours a week. If we actually take a look at how the PC processor usage sets up here, one thing you will notice is that you can actually probably just use SSE 4.2 and 4.1 now. These numbers were not so favorable 3 or 4 years ago. They were more like 70%, right? And so you had to be careful about using something like SSE 4. We probably just could use them now. I don't know if we want to make that decision or not, but it's pretty striking how much higher they are. So, you know, your mileage may vary, but we definitely could. Temporarily, we certainly can, but it's just worth noting that that's something we may want to replace. When you get to SSD 4.1, these floor and seal are built into the hardware, so you don't need to do any work to get them. And in fact, what they are is special cases of this particular function here. You can see, actually, if I go look at one of these, like seal SS, you can see that they all call the same function, round SS or round PS, whether you're rounding 4 at a time or 1 at a time. They all call the same function, and there's just a different immediate. So the way that it works is, instead of the old way, the same way that like the x87 worked and whatever, where there's a rounding mode, and when you go to round off a number, it uses that rounding mode, even if you are trying to do something else with it potentially. What this function does is it ignores the rounding mode of the unit and just takes an immediate that says what the rounding mode is. So this way you can floor, seal, truncate, so you can round towards negative infinity, round towards positive infinity, so that's floor and seal. You can truncate towards 0, which is like the C runtime libraries, or the C language way of converting a number. Or I think there's one more, which is you can round to nearest. So rather than biasing in a particular direction or towards 0, towards negative, positive, it's just whichever number is closest, right? So I believe you get 4 choices there, and you can see what they are. Yeah, here you go. So there's round to nearest, round down, round up, and truncate. And you have all of those pieces of information, right? And what you can see here is there's also some extra sauce you can put in here, where if you wanted to do something like have floating point exceptions on in the SSE unit, but then for certain operations, when you're rounding, just say, okay, for this time, I don't want them on. You can actually specify that specifically. So it's kind of just a way of overriding everything you previously told the chip to do during a round, and it's awesome. I love this instruction. So if it really is the case that we can use this now, I'm certainly a happy camper, to say the least. Like if the new world order is that you can use up to SSE 4.1, I would be delighted, because that just gets rid of a bunch of like weird 4 to 5 instruction things you have to do to floor and seal numbers normally, and replace it with just one clean instruction that tells the chip exactly what you wanted, but I don't know about that yet. Either way, like I said, because this is causing us a pain in the booty right now, I'm just going to go ahead and say we'll use it temporarily, and then if we want to replace it later, we can, right? Our square root's already doing this, right? And so now the question is, all right, can we just go ahead and put some other stuff in here that would fix it? So here's our functions. We've got them all here. We've got round, right? There it is. We've got floor and seal. And you can see that we're still calling the C runtime library for some of these. So what I'm going to do is I'm going to go ahead and try just replacing the flooring functions with one of these. So I'm going to go ahead and say round SS, because again, we don't need the PS version because we're not doing 4 at a time. We're only doing 1 at a time for these particular things, right? So for flooring, I guess I'll use the intrinsic, even though we could just call the round intrinsic and pass it the right thing. I'll actually just call floor SS. And what you can see here is when we call floor SS, it's going to do a rounding for, it's going to do a floor on the second value that gets passed in on the bottom. And then the rest of the bits will just be whatever are passed in here. Now, we don't care what the rest of the bits are. So, it doesn't matter what we're passing there, but we have to pass something there because that's just how the instruction works, right? So we can pass it as 0 for the thing that we're flooring, and we can go ahead and load in a single value here for the value that we actually want, right? And so what this will do is this will do the flooring operation, but we still have to get it out. And so this part still needs to happen, right? So although we have to kind of smush all those together, that by itself will now do the complete floor operation. I'll put a to-do in here. Because we don't necessarily know that that's something we want. But once we, if we do make that statement, then as you can see, these are very straightforward, right? And so, yeah. And in theory, everything just works exactly as it was working, right? There's no difference there, right? So those are really, really easy implementations of floor and seal because you don't really have to think. We don't have to go figure out how to do a good flooring or sealing operation ourselves, which is what we would have had to do before SSE 4.1. And so, yeah, if you can get away with SSE 4.1, definitely do what I just did. If you can't get away with SSE 4.1, which we have to see whether we can or not, then you have to think a little harder about it. But it's definitely, either way, it's not like sine or cosine. It's not as hard to implement as something that's actually going to require a bunch of math thinking to do necessarily. So anyway, back to our regularly scheduled program here. Oops, I do want to restore that breakpoint. So when I stepped through here, I just wanted to see what was going on with our debug string here. And I guess it's not going to let me step through that macro, of course. So I guess we won't really be able to see much about what that event pointer looks like because, of course, it doesn't want to tell us what the event pointer looks like, which is unfortunate. What is kind of nice about that, however, is I could force it to. If I wanted to, because we know the type here, I could make a little function that we definitely are going to hit, right? So, you know, I could do something a little bit more specific there, right? Like I could make one of these specific to this type and make sure it gets called. Let me also see something here. Because we're setting value string pointer to whatever the value is that's passed in, which is exactly what I want it to do, and we're trying to print that out here, but for whatever reason, something bizarre is happening to us somewhere down the line, and I'm not sure why. I want to kind of stop here, I think, to verify that I'm right, that that's what's actually getting printed out in the first place. Because I don't actually know that, right? So let me just go ahead and take a look at that. So if I just stop here, I want to see if that is in fact the thing that I was thinking it was. There we go. So let me open this up. So it does look like that was the thing I was thinking it was. So at least now I can look at this event a little bit more carefully, right? Oops. So here's the event that we supposedly recorded, and you can see here that the string pointer is set to null, which doesn't really make a lot of sense. The grid is correct, the name is not. So for whatever reason, this didn't get processed properly, right? The debug type string didn't get processed the way that we would want. Now, maybe that's just because I'm using an enum range here. Let me take a look. Where's the set of these guys? Here they are. So let me just do a quick check. So anything other than the types that come in here always get shunted down to the standard storage format, right? Yeah, and all of these things, yeah, so I mean, I don't really know why that would be causing a problem. All of these things are, you know, the 8 wide pointer for the value string fits just fine in the space that we have here for all the rest of our stuff. So there's no reason why it shouldn't have been propagated properly. But yet it's like not even parsing the event information for whatever reason, and I'm not really sure why that would be. So if I take a look here at init lighting. So let's say I call a nearly identical function, and then we run it. Oops, I don't want that. If I open up our debug view now, so it does look like for whatever reason, this part of the pass is just busted, right? So inside here, in the generate lighting pattern call, we're just not getting our debug printouts properly. Like its ability to record those is somehow hampered, right? It's not able to record those the first time through, maybe because they're only done the first time through, or something weird, right, is happening there where it loses the ability to track those somehow. You know what I'm saying? The name like goes away or something. So it looks like it's a per frame problem. If I went, you know, outside to something that gets called every time, so like compute light propagation, right? And I do this. I suppose I can also you know, all of a sudden it's like correct. So it seems like we've got a thing where we can't just issue something one frame and leave it there, which doesn't make a lot of sense to me because I didn't know we were doing that. Meaning I didn't know that we had like a decay on things in that way when we actually go to record debug events. So I'm not sure why that would be the case, but obviously it is the case. And so if something doesn't get hit on a subsequent frame, it's like it doesn't really get saved somehow. Because it's never going to trigger one of these again, right? It will never be seen. It's only being seen one time in collate debug records. So it shouldn't really ever go away, I don't think. Unless it's just eventually it gets removed because it gets used for something else, right? But even that I don't think is the case because, well, I guess it might be for the actual value. Yeah, I guess I could see that. So for now, I guess I'll say, all right, that's okay. But I don't love it. So I'll just store the name here. And that should be that. So when we run now, hopefully we can see it correctly. There's generate white noise samples. And so if I make a you know, some kind of a function here, where I'm just going to say, hey, lighting pattern something like that. When we do those F key things, we had like some in here that would cycle through. Let's just, instead of doing this, if we hit the F9 key now, what I'm going to do is say generate lighting pattern. And pass it like just an index that just goes up, right? So now, at least in theory, right, if I come in here and I look at this lighting pattern, it's white noise samples. If I switch to polar samples, then I get that, right? If I switch to spiral samples, then I get that. And if I switch to Poisson samples, then I get that. You know what I'm saying to you? And I guess the first thing that I would point out is actually it does exactly what I wanted. So using the stratified sampling, the amount of noise has dropped dramatically, right? Like the flicker is way, way less than it was. And the lighting is much more consistent. Like that actually looks really good, right? I don't remember how to stop drawing the debug lines, but I think there is a way to do so in here somewhere. Maybe this one, although I think that just stops them from updating. I don't think that stops them necessarily from drawing. I'm not sure. Yeah, I don't think there's any way to do that, unfortunately, at the moment. So that was supposed to, F2 is supposed to stop debug lines from being used. What's going on there? Oh, well, that'd do it. So again, just cycling through these now. So there's white noise. There's polar, which doesn't have noise in it right now, so it's not really a good test. Here's spiral. And here's Poisson. And that looks pretty nice. I mean, I don't know about you, but I'm pretty happy with that. And that's entirely CPU side right now, right? Like, we're not using any GPU for lighting at the moment. You'll also notice that our speed has taken a hit, right? And that's exactly what I was saying before about how, we can't... we have this problem where we're not bundling our arrays at the moment. So it feels like we want to do that bundling as well, just to make sure that we get our speed back. But otherwise, I feel like that's pretty darn nice. And I'd be interested to know now if we just introduce more lights back in the mix. How we're doing. Where's our snake? I don't remember if this still has lights attached to it or not. Yeah, so now the snake should be adding some light, and it is. You can kind of see it. And what happens if we make it be brighter? I don't know. Unfortunately, I don't actually know what add piece light does. Emission. So, you know, I could make the snake really bright. And you can kind of see, like, so you can see some of the bugs in the way, well, not like bugs, but approximation cost. So we need to do probably some more work on our aggregation, because that's working pretty well now, but you can also see that it kind of like, as it aggregates the lighting in an area, it spreads it too much in the case where the aggregate lighting gets summed up into a box that then gets used by someone who's further away. You get some error in there. So we want to tune that probably, you know. But you know, like, we really take no hit from adding, that was adding 6 more light sources, right? And it just works, which is pretty great. You know what I'm saying? And so I think that's nice because it means, you know, we have the option to just like throw lights around however we want. And we don't really suffer performance penalty because we're always convecting light every frame for every surface. So it's not like we're doing something that has a per light cost, right? At the moment, we're also like, so I got to switch back to, I got to make it so we default to the Poisson. I think I want to use the Poisson version of the lighting, but we're going to improve it a little bit too. So let's go ahead and switch to Poisson by default. Since I think that's the one I want to go with just based on looking at them. So here's the Poisson-based version. And right, you can see how it overlights that area because of that distance. And we don't know what that distance should be set to, right? It could be that we just need to set that distance a little higher and then it's fine. But it leads to errors because we don't do like occlusion to figure out like whether or not you could see the lighting that's supposedly coming from there. So we have, you know, we could do more work on our construction where we build those boxes of light distribution that would prevent having errors of that form. Now, you know, again, in a game, it's hard for people to know that that really is an error sometimes, but, you know, so you got a lot of leeway there. You just want nice effects. They don't necessarily have to be accurate, and especially with something like lighting. But it's just like you can kind of see, like, that light is coming from up here because it's casting to a box that's a little further away. And so it might be that, like, you know, that's just, that distance is too low, right? So if we come down here, we probably don't need this anymore. Just simplify that. So if we take a look in here, we've got the close enough thing. So this T close enough, you know, maybe that's more like 10. I don't know, right? And it's hard to say. We'll have to tune that value and see what our performance looks like and see what our stability looks like and so on. But if we do something like that, and we're going to have to make sure we're bundled first to evaluate the real cost. But if we do something like that, then we'll get a lot less of those errors. So now the lighting would be much more accurate than it was before because it actually does much more localized occlusion, right? And so now, if you look up here, although these people are still lighting up there, they're not lighting down here because these people correctly pick up these as occluding them before checking for lights that are aggregated somewhere else, right? So that's just worth noting. But again, looking really good. I mean, I'm really happy with this. I think this is pretty awesome. And I think I would go ahead and press forward on this. Now, we still have a little bit more we can do here. Obviously, like I was saying, so this sampling is not cosine biased, and we still introduce the cosine bias. later. So we could probably still fix some of that. So if we want to, and then we have to do our bundling for speed purposes, right? So if we wanted to generate, so we're using the Poisson samples here. If we wanted to generate Poisson samples that are cosine weighted, there actually are some other ways we can do it. And in fact, we can make our Poisson generator probably a lot better than it is right now, too, by taking advantage of some opportunities that we have here. So let's talk about those and maybe go ahead and implement that, right? So if we pop back to Milton for a second here and do a little bit of drawing, one of the classic ways, and this has been brought up on stream as well, but one of the classic ways of doing cosine weighting, if you know that you can generate things in a disk pattern, so one of the classic ways of generating something that's cosine biased is if you are trying to generate cosine bias, and by cosine bias what I mean is if we are looking at the hemisphere, we know that we're going to very low weight things that are in these directions, and we're going to high weight things that are in these directions because of the way that the lighting shaft falls, the amount of light that gets collected from things in that area. It's the rule, remember we drew it out, the amount of light coming in from this right triangle, right, versus the one coming in from here, right? The size of that aperture is very different. So if we know that we want to have that weighting, what we can do is take that weighting out of the light propagation function, right? Because right now what's happening is that's actually, this angular fall-off term here is doing that inner product. What we could do instead is just get rid of that, right? So we could say, you know what, the angular fall-off isn't going to count anymore, right? We're just not going to count it anymore. And if we were to do that, now we would be getting essentially an erroneous light, it would be wrong how much light that we're actually getting in the scene, unless we then bias our sampling to always go biased towards samples that come from higher up, because we can basically put the cosine term into the sampling bias rather than just something that happens after the fact, right? And so in order to do that, all we really have to do there is say, okay, if we're going to bias our sampling in that fashion, we now need these functions to really put out things that are biased cosine, weighted towards the cosine, right? So in order to do that, again, for Poisson samples, which I think is the one we want to go with, it's pretty straightforward for us to do that, actually. One of the techniques for it is to say, well, why don't we just say, let's generate things in a Poisson pattern on a disk and then project them up. Because if we project them up, then what's going to happen, you can kind of see here if I draw it in 2D, what's going to happen is most of our points, right, that are close to the edge here, they're still going to project up quite a ways. And most of our points that are in the center will sort of still stay in the center. So it's very hard to produce things down here because the upward projection means you have to be really close to the edge to get it. Whereas it's really easy to produce points here because any point at all that was roughly in this shaft is going to project right on up to there, right? So it creates a natural cosine weighting by projecting it up to the sphere. And so what we can do is just generate things in a disk and then project them up to the sphere. So for starters, what we can do is we can generate our sphere and project up as two separate passes, right? So let's change our Poisson generator to do that. So what I want to do is, you can see here, we're running like the lighting equation and all that, and that's all well and good. But what I'd rather do at the moment is I want to go back to the thing where we were drawing these things, and so I can see the distribution and make sure that we're doing it properly. So if we come down to this code here, and we take a look at how we were drawing this stuff before, I want to re-enable the one that was just like putting, oops, that's not what I wanted at all, I lied. I want this one. And I want this one to draw our sampling pattern. So what this is going to do is this is going to go ahead and take however many of these are in one of the sample point patterns. We're going to go through one of the sample point patterns, and we're going to grab out each of the sample points, right? And we've got 4 per. So the component index, here we don't really need this color table thing anymore. For any particular reason, I'll still leave it in there, but this is not particularly relevant, obviously. Anyway, if we did want to put that in there, we can do 4 times point index plus comp index. That would still get the alternating colors. Anyway, so if we want to grab out the normal here, we can look at the sample point patterns that we have. We're going to just draw the 0th one, and we're going to take the point index out of that. We want to do a get component on it so that we can just get a v3 out of it. So then at that point we draw it, and we're good to go, right? So that's just reinstating the thing that draws these components, that draws the sample pattern, so that if we go in here, let me get this out of the way. If we go in here, we can see our Poisson pattern. That's what it looks like at the moment. And so now what I want to do is I just want to generate a disk worth of data. So I want to generate a Poisson pattern, but I'm going to generate it on a disk. Okay? We'll see how that works. So I'm going to go to generate Poisson samples. And on here, what I want to do is generate things in the disk. So what I want to do is just keep the same while loop here. But when I do this v3, what I'm going to do is I don't care what the z value is. Okay? So I'm just going to generate these in a disk. Instead of measuring by the cosine, I'm now going to measure by the distance. So I'm going to say, like, okay, there's a dist value. Wait, what was that doing? Oh, that was just spreading factor. Yeah. So all I'm going to do now is say I want to take the distance. So I'm going to take the length squared, we might as well, of the one that we're checking here and the one that I've produced. And again, we know this is now just in 2D because we know the z's are always 0. And I want to make sure that if it is less than, so that the length squared is less than the minimum distance squared, then I want to throw it out, right? We stop at that point. So I just need a value for minimum distance squared. And again, this is just a constant now. I don't know what that value should be because we're trying to pack 64 points in here. I'm not sure what it should be. You know, maybe it's 0.1 or something like that. We'll know if we can't actually run successfully. What is the question? Oh, sorry. That's supposed to be a minus. There we go. And so let's see if we can get this going. Okay, so that's too small. So now we should see a point here. Oh, yeah, that's why. We don't want to normalize these yet. There we go. So this will go ahead and produce our disk, and sorry about that. Afterwards, we'll figure out how to loft them out. But yeah, so let's try that one more time. All right. So here's our random samples, right? And they're not conforming to a disk at all. So that's fine, but they're also not really very Poisson distributed because this is probably too low. So the first thing we want to do to get this to the place that I wanted it to be, which is a random hemisphere sampling cosine-weighted, is now we want to reject anything. Oops. We want to reject anything that's not in the circle, right? So we want a unit circle. So if we find that, in fact, I can just use the valid here. If we find that the x squared, plus the y squared is greater than 1, that means it's outside the circle and we want to throw it away, right? So since this is supposed to be valid, it needs to be inside, so we really want less than or equal to 1. But that will constrain us to being inside the disk. And so now if we look, we only have points that are inside the disk, but they're not very well spread out. And again, that's because this value is probably too lax. So we need to enforce a higher distance constraint here on these. And so now it's starting to spread out a little bit better, but still not great. And so let's keep going, jack it up a little bit more. Still not quite good enough. Now we're starting to get somewhere, right? That's starting to look okay, but I still think we want to probe for the crash point. There we go. So that's looking real nice, right? That's looking like a nice distribution of points, right? Pretty even. Looking good to me. Oops. Let's see how 1.7 is. I assume that's too high. Nope, not quite. So that's a real nice distribution of points right there. You know what I'm saying to you? It's looking good. So now what we want to do is project those up. And if we're going to project those up, all we really have to do is just run through our disk now and do exactly that, right? So we have a dest index, and we go through all the points. We then say for each individual point, let me go ahead and grab it out. So what we want to do is modify p here to project it up. We know this quantity again, right? And to be fair, this is really just the length of p. So, you know, if we wanted to, we could just say that. There's no real reason for us to write it out. So this is actually, you know, a shorthand way of saying that. And you can see we still get the same results there. So then what we want to do is say, okay, if that's our length squared on p, then what we want to do here now is take our destination index, run through those, and do the same thing. So we know what the length squared of p is here. And we want to write an equation that will project us up to the correct height to fill in that gap. So what we know about our circle here, let me just swap it here so we can draw it. So we know effectively that we have some point, right? And I could do this in sort of a 2D diagram. We know that we have along one of these axes, let's say the x-axis, we know we have some point, right? And we know we want to project it up here. So if we were only in 2D, right, how would we do that? Well, we know that we want the resulting vector to be unit length, right? And so, and if it was unit length, it will be by definition on this sphere. So what we need to do is say, okay, if it's unit length, we know that its length squared that we were computing, right, has to equal 1. Right now, we know it's less than or equal to 1. It is not equal to 1. So what we need to do is fill in the z value. Because remember, we're projecting up to the sphere, so the x and y can't change. We just need to fill in the z value such that we account for the rest of the unit length, right? So we want to say that our x squared plus our y squared plus our z squared, right, where these two are known and this one isn't, we want to say that that has to equal 1 because we want this to always be unit length. So if we then solve for our z, right, we're going to have 1 minus x squared minus y squared, and we're going to square root that, right? So very, very straightforward. This value here is the same as that, right? So 1 minus the length of the vector currently square rooted is what the z has to be set to. Does that make sense? So we already know what the length squared is of this thing. That means our z value, or I could just set it directly, is that. Oops, not quite that. There we go. And now we know that we have a properly normalized vector as a result, if I didn't mess up the math. Always a possibility. So going back to our visualization now, we should see these things nicely on a dome, and we do. So in theory now, we're getting, this should be cosine weighted in terms of our samples. Let's take a look and see if it really is. It's a little hard to say just how cosine weighted that actually is. Kind of want to be inside the sphere looking out for this. You know, but it does seem pretty good. So I feel like, you know, it seems pretty good. I don't really know, though. So what I kind of want to do is check. Does that make sense? Like, what I'd like to do here is see whether I think it really is weighted or not by just summing up all of the samples and seeing what we get, right? Because we should be able to actually do a summation over the sample points and produce a value that confirms how cosine weighted it actually is. Does that make sense? So if I was to do the integral over the sphere, or even just do a test, I guess one of the problems is how many of these, you know, are you going to do exactly, and so on. If I was to take the integral over the whole sphere, right? I mean, over the whole hemisphere of something that was cosine weighted, I get a particular numerical value out. If I do the same thing on my supposedly cosine weighted set of samples and do a summation of 1 at each point instead of the angular fall off at each point, I should get similar results. So let's try that. I also would like to turn on those debug lines real quick. So here's the casting. Not quite sure how this is getting lit. Because it's only looking downward. I wonder if we have a bug in terms of the directionality of light somewhere where that, because that should never hit anything. I'm interested to know. I want to move my sampler down there, actually. Let's do that right now before I do any more with the cosine. So let's suppose that I move this guy around. Debug point location. And I want to move towards the blue. I just basically want to be under this blue thing here, right? So let me move, I guess, back. Oops. Not sure where my debug lines are at the moment. There we go. So that's just straight up pointing the wrong way. Like, it's able to shoot things out the back somehow. But I don't know how. And you can see it is trying to shoot things out the bottom as well. So it's shooting things off of it in every direction. So that's a very interesting bug, and we now have a good test case to... And I'm going to leave this locked in here, because that should not be happening, right? So what is the normal at this point, is my first question. Let's go take a look. So here is, the normal. Here's the X and Y axes. So the first thing I'm going to do is I'm going to change the way this is being drawn. What I want to do here is I'm going to use a cyan line for a hit and a yellow line for a miss. Okay? So those should all be yellow, and those should, all these ones that are sampling the interior here, this should all be cyan, right? Let's see that happening. Then what I'm going to do is I'm going to draw a coordinate system so I can see for the sample point what its coordinate system is. So I'm going to grab this push debug line situation here, and rather than drawing anything per ray, I'm going to just draw something per point here for the sample point. So when I hit this sample point that I wanted to know about, I'm going to push a few debug lines on here. And these are not going to be colored by anything. They're going to be rote, actually. And they're going to go from the position of the sample point out along a vector, like so. And I'm just going to draw all of it. Oops. So this would be the world axes, right? If I wanted to see what the world axes were. But I don't want the actual world axes. What I want is the axis for this point. And it turns out we actually have that information, right? That's what we're using to base our cast off. And I want to see whether it's right, because maybe it's just wrong. And if it's wrong, that explains why our construction is bogus. Oops. So here's our coordinate frame based off of the sample point. And now I can look and see what it actually has. So looking here, you can see that actually the coordinate frame is very good. It's exactly what I would have expected. So although our coordinate frame is very good, our ability to place our samples is not, right? So now we kind of have to go in here and look at this situation, because this is borked. Whatever is going on here is just wrong. Okay? So we have to figure out what's going on there. So let's take a look at what we've got here. So our sample 4dx value is pulling out 4 sample points from our sample point arrays. And these sample point arrays should all be normalized so that they're pointing upward, right? So if we take sample point dx d4x.z there, right? And I don't know why we still call it d4x, because we don't really need to. Like, I could call it something else, I suppose, but well, whatever. So if we want to figure out what's going wrong here, we have to figure out, look, why are we getting this weird, why is this weird behavior happening? So this is supposed to be lofting the normal up and the xy axis into something that we can use as something that operates across our entire set of vectors. We have our sample points here, and these should allow us to move along the x, y, and z axes such that we effectively transform the sample into the right space, right? So we would expect to be working to correctly transform it to align to the normal, but it doesn't appear to be doing so, right? It doesn't appear to be doing that at all. So the question is, why isn't it doing that, right? And I have no idea. Now, I suppose one thing that I should point out here, actually, is maybe we have a bug in our raycaster that's allowing rays to cast backwards. Oops. If that's the case, let me even give it a little bit of an epsilon here, but I think it's looking bad, right? If that's the case, then really, yeah, we're oriented properly, perhaps, but we might be actually doing everything right, but our raycaster's busted. Where do we check to make sure that a hit has to be greater than 0, right? And the answer appears to be absolutely nowhere. Right? I mean, here we are. I like we have pre-invert the ray for more speed, but it is pre-inverted, so that's... you know, we come through here and we're looking to see if Tmax is greater than 0. So where, if any of these are true, if any of these pass, then we're going to get inside here, right? And this T-valid, I think this T-valid actually needs this case. Right? Because what was happening is certain times you would get a max pass on some other ray, and it would allow a T-min that was negative to sneak in here. Right? Which is incorrect. So I think that's what we were having happen there. Much, much, much better. Lovely. Okay, so the first thing to note is, well, for starters, I'm absolutely loving how good this is looking. But the first thing to note is we got a lot brighter when we turned off the angular fall off, right? Which suggests to me that our sampling pattern obviously is not, well, it's one of two things. Either our angular fall off was messed up and was taking too much light out of the system for no reason or something, right? So, you know, we don't know that that was correct. Maybe it was buggy. But the other thing that might be happening is our cosine weighting is not proper, right? So I still think we want to then go investigate that. But at least now we know why we were getting those weird backcasts there. So that was just a bug in the optimized routine. So now this all looks good, because now the only coloring you see on the bottom where there shouldn't be any light at all is coming from if it's just a plate that actually was taking a sample like up here, right? So that's valid because the sampling was actually coming out of like right here where it could see a light. And it's just, we don't actually check to see that the pixels down here were, not obscured by something, right? Because we're not raycasting per pixel, we're raycasting per plate. So that all seems relatively straightforward, right? So I'm happy with that. I just want to know why we didn't have a similar amount of light when we switched between the angular fall-off version and this version, right? And so I think we need to maybe get more work. We have to do more work to get the cosine weighting to happen. I think so. Here's another problem that I think we may run into. Although white noise on a disk lofted up might produce a pattern that's going to be cosine weighted, that doesn't mean that blue noise does, because blue noise has the artificial property of forcing coverage into areas that wouldn't normally be filled by random samples. So I don't actually know if this is a really good way to do that process. So it may be that our previous way of doing this is actually better than the disk method, even though the disk method would be good for the white noise version. So I just wanted to kind of point out that I think we have to do more analysis to really even know. Now, I don't know where we're at for time today. We got about 15 minutes left, I think. So yeah, I think that's fine. So we got about 15 minutes left today, so we need to do, like I said, 2 more things. I'm not going to try and do the bundling then. We'll save the bundling for next week. And I'll go ahead and put that down in here. Where is that? So that should be fine. What I want to do here is I want to now take a look at that to see what that weighting actually ends up being, right? So what I'd like to do here is say, let's figure out how to do a sampling comparison. So let's suppose that I wanted to create, I don't know, a quote-unquote ground truth version to see what happens if I take a certain number of samples and I want to generate them randomly, and then I want to do weighting, right? So I'm going to go ahead and do I need to do some way of generating a random sample on the sphere, which I need to actually be unbiased. So what I probably can do is, if I generate any random vector and throw out any vectors that are outside the sphere, would that give me an unbiased sampling of the sphere? You know, it's hard to say. I'm not sure how to analyze that. What I was basically saying is if so like pick a random direction. If the direction is greater than 1, I should say less than 1. Right, so this produces a set of directions for us. And then what I want to do is take a look at what the inner product of those is. So unweighted, right? What I want to do is make a test sum here. And I want to, and in fact, maybe I want to do this. Let's run some tests where we do 64 samples. I don't know how many times we want to run it. A lot. We will do the sum. So as we loop over these, I want to do a weighted product of something. So I just want to see, okay, what's the inner product as we were doing it before, the angle inner product here. Oh, and I also want to do if dir z is less than 0, dir z equals negative dir z. So I only want things pointing upwards because it's a hemisphere. So I want to take the inner product of the direction and I guess I just want the inner let me just go ahead and take a look at what we were doing before, make sure that that made sense. So the angular fall off was yeah, it was just against the surface normal. So it's really just that, which is z. So it's really the direction z that I want to sum, right? Because the inner product is just going to pick out just that z value. So what we were previously doing is we were basically multiplying by the z value, right? Which is the cosine of the angle between the two, the direction and the normal, right? So I want to sum all these up. I'm just going to sum up how many of these we have in this case, right? And then at the end, I'm going to say the min test sum. And I can do this normalized by the number of samples as well, I suppose. So I could say, like, you know, sample count equals 64, sample count. And then say, like, you know, average equals test sum divided by sample count. Min test average equals and I'll just keep whichever ones is correct, right? So that gives me like bounds to look at for if we were going to take 64 sample points. And the reason that I'm doing it this way is I just kind of want to know, generally speaking, I want to know if I was to do a summation using the angular fall off, but only using 64 samples, which isn't a lot. If I was picking them randomly, what would I end up with in that case? And then here I can do the same sort of thing, right? So then when I come over here and generate all of these, when I come through them, I can summate, I can summarize, it's just sum. I can sum up all of the values that I get here in the exact same way and see if, without weighting them, they end up equaling the right amount or a similar amount, right? So off we go. So what I want to do here is just say that whichever one of these is z value. Before I was doing test sum plus the dir z value, right? Wait a minute. So in order to do this, I really do need to know, though, some other function that I'm sampling. So yeah, if we were going to weight a function by that, then this one should just add the function directly without weighting it, right? And I'm not sure how to put that in here. Because I need some other function, right? So what I want to do here is say, well, what, the function of x, y, z, I want to be able to evaluate the function of x, y, z here, and then multiply it by dir z, right? So I want, that, right? And then here I just want to do that without weighting it by the z. Does that make sense? Like, that's what I'm actually trying to do there. And then when we actually do this, I want to see how these compare to each other, right? That's what I actually wanted. But without a test function, it's hard to know. I suppose it doesn't matter what the test function is. The test function could be anything. So I suppose I can just put something in here, oops, and say, well, the result is, dir x, 3 times the direction x plus 2 times the direction y or something. I don't know. Plus, minus 5 times the direction z squared. I don't know. Right? I mean, this is something I'm going to have to think through a little bit more, but we need some test function that's pretending the world has something in it, so we can see how they differ in these two cases. So I think that's what I want to look at. Something like this. So I can take a look at what the difference between those two things actually ends up being. So yeah, let's take a look. Oops. min test average, max test average. Well, the fact that those are not even close basically tells us that we're just undersampling this thing pretty badly. So, you know, there's that. Which means it's going to be a little bit hard to do this test that way unless I just got a bug in the code. But that's, you know. Also, this is not quite right if we're allowing negatives in our functions. Let's try that again. So yeah, I mean, not great, right? It's a pretty big span there for only the 64 samples, which, yeah, I don't know. Maybe that just means I'm bad at sampling, which I think we already know. So let me just take a look at what our min average and max average is of this function. So yeah, not great, right? It looks like it's, you know, its lower bound is similar, but its upper bound is not, you know. Which, again, you know, this is a pretty crappy test, but that does comport with what we're seeing in terms of the, you know, the difference between those there. So let me try a couple things here that I'd like to then play with. So let's suppose that we wanted to look at the white noise samples. Here we go. So if we think that this technique was working okay using the disk, what we can do is play with it a little bit and see if we can do a white noise that's biased as well. So doing that would be much simpler. All that would be is we loop picking a random sample in the disk. So that's just saying, okay, pick a random sample in the disk, like so. If length squared p is less than or equal to 1.0, then we're good to go. Pz equals square root 1.0f minus the length squared p. So that just allows me to generate the random value, actually random values in the disk, and then project up to the sphere, right? And that's the more traditional route. Actually completely random. So now if I run it and take a look at what happens here, because remember now we're using the white noise samples, and I just want to see what the difference is there. So you can see it's a pretty different. It's pretty different than this version. The problem is I don't know how much to trust this version. -7, -0.7, I'm sorry, and 0.15 is still quite a bit different than the Poisson samples. So even if we just compare white noise lofted up versus Poisson lofted up, you get a very different answer, right? And again, that may just be because this is a bad test case, so I don't want to jump to conclusions about it, but it means we need to investigate further, right? We need to drill down to this a little bit more and figure out what's going on here, because it's not quite, yeah, it's not quite kosher yet. This might not be a good way of generating unbiased samples on the sphere. I need to think of how to generate white noise samples on a sphere that are unbiased, because this may not be it. Otherwise, also, I should say, this may bias you still towards a projection of a cube, and I'm just not sure if it does or if it doesn't. Hard to say. Anyway, let's go to the Q&A, but next weekend I think that's where we want to focus our attention. How do I gotta get a screenshot of that. The fact that Instabot said Blow's avatar looks exactly like him is kind of amazing. Did it put that together by itself? I don't know how it did that, but that was pretty great. Vadafrifo. Hi, not really an on-topic question, but you said you'd talk about some tidbits concerning the SIMD union type. Ah, yes, I can. Okay. Let me double check. Let me see what we have for questions here really quick. All right, let me answer these other questions really quickly, and then I'm going to spend a little bit of time talking about the SIMD union type. So, Risco, how are you feeling about the progress of the lighting so far? Very good. I like it. I like it a lot. Holst 80, is there any libraries available that would help with just the lighting stuff if you're working right now? It seems fairly involved and required some R&D from the developer's part. No idea. I don't use libraries. G-Princip, why are you not sure about GPU lighting? Do you think that it might not increase the frame rate? No, I'm quite sure we could get faster lighting by using a GPU. What I'm not sure about is whether we have the GPU to spare, because if we want to use the GPU for doing a bunch of other stuff, then, you know, you want to balance your workload, right? So we don't have necessarily a lot of stuff to use the CPU for. We aren't doing like physics-y sorts of things in this game. This game is very mechanical and not supposed to have a physics component to it. It's supposed to be very predictable, like an old school arcade game. And so the reason that I don't know if it's a good idea to use GPU lighting is because we may just end up with a giant GPU workload, because it does the lighting, the depth handling, the, you know, anti-aliasing, all that sort of stuff. And at that point, we just end up with a CPU sitting idle doing nothing and a GPU that's overloaded, right? So the only reason I'm not sure about GPU lighting is not because I don't think we could do a reasonable implementation of this lighting on the GPU that would be fast. It's because I'm worried that we will overload the GPU and have nothing for the CPU to do. And that seems like a bad situation to be in. So, what do I dislike about Windows 10? Some people complain that because they're hatred against Microsoft regardless of how good the product is, but I feel like they Mixed a lot of messy stuff after 8 and 8.1. What are the things you'd like them to fix? So I would say Windows 10 is a complete non-starter. I would never use it for any purpose under any circumstances. I had to install it on this machine because it was a brand new machine, so I was forced to. Otherwise, I would never do it. It is completely unacceptable for an operating system to force updates, period. That is a hard... If an operating system requires you to update it when it tells you to update, it is unacceptable. I don't need to know anything else about the operating system. You can tell me just that one piece of information, and that is enough to know it is unacceptable. An operating system on my computer obeys me, period. If that relationship ever changes, it's an unacceptable operating system, period. So Windows 10 is not allowed at Molly Rocket. It will never be installed on a computer here. I only use Windows 10 on the stream computer because it was a new computer. If we cannot find a way to install something other than Windows 10 on new computers at Molly Rocket, then we will either switch to Linux or find some kind of hack that allows us to use an older version of Windows. We may be able to use Windows 10 at Molly Rocket if it turns out that disconnecting Windows 10 from the internet, since our dev machines don't hook up to the internet, makes it so that it doesn't produce the forced updates. But if that still is the case, then it's a non-starter. So we don't really need to talk about anything else. I could go into a long list of reasons that I don't like Windows 10 that are separate from that, but it's that one that's how you know this is not an acceptable operating system. Done. A operating system that ever pops up a dialog box, actually, is unacceptable to me. If you want to notify me that there's a new update, put that somewhere else. You can put that, put that down here. That's the only acceptable place for it. It should never pop up anything in the middle of my work. That is just a complete disrespect for the user, and it should never be allowed in an operating system under any circumstances for any reason. And I don't want to hear any comments about security. I don't want to hear any comments about anything. Those are my decisions. This is my computer. Microsoft doesn't get to tell me when it gets updated. I tell Microsoft when it's updated. I accept the responsibility for using my computer, and if they don't like that, then I'm going to have to buy an operating system for somebody else. It's that simple. How many hours a day am I programming? I program probably no less than 6 hours a day, and usually no more than 10. But it varies, depending on my other responsibilities as well. Do you think we'll be able to keep the lighting at this complexity or method on the Raspberry Pi? Probably not. I wasn't expecting to run anything like the real game on the Raspberry Pi. I'm expected to have to turn off a bunch of features because it's very underpowered compared to a PC. What level are intrinsics defined? Are intrinsic CPU vendor specific or architecture specific? Will we need to make AMD Intel specific intrinsics or x86, x64? We don't really probably support x86 anymore because nobody uses it anymore, so we probably don't have to do that. x64, no, you do not have to have AMD or Intel specific intrinsics. They work across the board. We will, for Neon, which we will probably want to do a port to at some point, have to make our intrinsics be agnostic between Neon and x64 because Neon does have slightly different instructions, although they are similar, right? I understand you switched from AMD to NVIDIA. Any specific reason? I always prefer NVIDIA because they seem to have more stable drivers and easier to use performance tools and so on. So given a choice, I go with that. The reason I was on AMD before was because that was an old surplus machine that just happened to have an AMD card in it. It was not a machine that I had put together myself. How much longer do you expect to spend on lighting? As long as it takes till I'm satisfied with it. Sorry for an off-topic question. I'm pretty far behind. I'm curious if you've already implemented the swapping function or macro. How would you avoid using templates for this? You mean to swap two variables? I usually just write it custom for the ones I want, or if you want to write a macro, you can, but it's not particularly an interesting... I don't really care. That's not like something I spend a lot of time doing. If you want a swap function, you can just write it, and it's not a big deal. All right, so let's go back to the original question. And that question was... In our definition of our sort of like easy to use or easier to use SIMD types here, the question was, do we actually have to use the convert macros or can we just use this, right? And when I was asked whether we could just use this, I said I can't remember if there's reasons why you can't, but I do remember there was something weird about this. And I went back and checked with friends of mine to find out about whether or not I was misremembering, and I was not misremembering. There is something weird about it, but it's okay to use the union. So, answer 1, it is okay to use the union. Nothing weird will happen to you. However, there is something weird about it. And let me now tell you what the thing that's weird about it is, because it's worth understanding. So, you may notice, if I go into the Intel Intrinsics Guide, and I light up all of our SSEs that we might be using, right? SSE, 1 through 4.2. Let's suppose I look at the OR instruction. You will notice that there's more than one OR instruction per type. I'm sorry, total. There's one per type. Here is an OR instruction for doubles. Here is an OR instruction for singles. And here is an OR instruction for integers, right? Now, the really unusual part of this, and the part that's the interesting part that I said I want to elaborate, the actual instruction is not the same. Do you see that? Now, why is that, right? And you can see here, even the performance is not the same. It changes, right? So what's going on here? What's the deal, right? And the answer is that even though these types are not really relevant at the CPU register level, because the registers are the same whether or not they're being treated as doubles or singles, or integers for that matter, that's not true of the actual arithmetic logic units that will execute them. So, inside the processor, we have logical registers that we're referring to by name. XMM0, for example, or something like this. And it's true that when I talk about XMM0, I can talk about it either as an M128 or an M128i, because the only difference between those two things at the register level is what I want to do to it. So if I say, for example, I want to add an M128 to another M28, I'm talking about adding, say, a floating point value perhaps, whereas if I talk about adding an M128i to another M28i, what I'm talking about is doing an integer add. Something like this, right? But I can still say XMM0 in either case, so it's not like I'm saying a different register. So that begs the question, well, why does it matter which of these I would be calling as a result? And couldn't I just use that union blindly and not care? The answer is you do care, because once the instruction is issued, it goes to a specific type of unit. Now, in the case of something like an add, where I'm going to add two floating point numbers together with an M128, then it's always going to the same type of ALU. It's always going to something that can do a floating point add. But if I am going to issue an OR instruction, it could go to either kind of arithmetic logic unit. It can go to one that can do a OR PS, or it can go to one that could do a POR, or one that could do an OR PD. Believe it or not, this actually makes a difference. There are units that do the, how should I explain this? So all the units could probably do an OR, but the question is, which one do you want it to go to? Do you want to do the OR on a unit that could have done a floating point add, or do you want to do the OR on a unit that would have done an integer add? And the reason this matters is because once you issue it to one of those units, that unit is tied up for that instruction cycle issue, right? So if I've just issued an OR on the F32 lane, on the F32 unit, right? Then I want to do an F32 add. Well, I might not be able to get it off that cycle because it's already got an OR, like blocking that reservation station or something, right? So instead, I could issue the OR to the U32 unit, right, that can't do an F32 add, and then I can issue the F32 add on that same cycle to the thing that would have done F32 adds if only it hadn't been blocked by the OR, right? So that is the important subtlety to remember when programming SIMD code on the x64, is that there are arithmetic logic units. They don't all have the same capabilities, but some of them have overlapping capabilities, such as the ability to do an OR. So if two logic units have the ability to do an OR, but only one of those logic units adds F32s, and only one of those logic units adds U32s, if you know you're going to be over-reserved on F32 adds, maybe you want to move your ORs to the SI 128 kind, or the vice versa, if you know you're going to be doing a lot of U32 adds, well, U16 adds, let's say, and you know those only go on one unit, try to move your ORs to the PS unit because maybe that is the one that is not going to get used as much, right? So, the takeaway here is you can use a union to represent a 128 and a 128i, but you cannot necessarily be cavalier about which one you use for doing operations that could be used by both. So you can't just say an OR is an OR, you have to be able to say which kind of OR you wanted. Now, I have not done much analysis of whether modern compilers will just switch ORs for you based on what it thinks is the loading of the units. Maybe they do, maybe they don't. But if we assume temporarily that the compiler can't always get that right, and that you do need to kind of give it some guidance about which one to use, that is where it makes a difference which one of these two things you're using. So it's not superfluous that they have M128 and M128i. It's not probably how I would have recommended to do it. I probably would have just had one type and then just had the two different OR calls, or to this unit or to that kind of unit or something like that. But either way, you can see why it does make a difference which kind of OR you're issuing, and it's something to keep in mind. Hopefully that gives some perspective. Let's see here. What are the specs of the current dev machine? It's a good machine. It's a Core i7... fairly high-end Core i7 with a 1080. I never remember these names. The 770K. In your opinion, what are the low-hanging fruits the Unix Linux world could or should tackle to become more competitive with Windows from a usability perspective? One, actually support laptops. Linux's laptop support is horrible. Largely, perhaps not necessarily because of their fault. They don't handle like Optimus graphics and stuff like that, which you absolutely need to do well. They do it very poorly. So you need to fix. They need rock solid laptop support, which they just really don't have. Audio is a mess on Linux. They need to just scrap everything and have a very simple, 100% compatible, used everywhere audio layer, for the love of God, and just lock it down and say, this is all we're doing forever. Please don't change anything else. They need to have a good debugger, like a really good debugger. They need to have very good GPU support, nice GPU speed, easy to use, like full screen GPU, all that kind of stuff. They just need to work on all of that, getting it really clean. Really basic stuff still doesn't work on Linux all the time. I have a vanilla Ubuntu install running on the machine I'm looking at right now that runs the chat. It hangs the entire desktop routinely on drag and drop operations and right-click menus. This is a vanilla install on a stock machine with Intel integrated graphics. It doesn't even have a second GPU in the machine. It's just a stock 7700K. That's all. And it is extremely buggy. You just can't have that, right? It's gotta be a lot better than it is right now. People who don't think Linux is extremely unstable they have their eyes pretty closed. If you can't do a stock install and have drag and drop not hang your entire desktop, you have serious, serious problems. And so that's just a basic thing. I could go on for a long time about all the things they need to fix. They also need to fix the total non-standard way that everything is scattered throughout the system. Well, oh, which distribution are you on? Oh, okay, then these files are in a totally different place. Someone needs to be able to go to the internet and get an answer to their Linux question. It can't be, oh, well, the answer to your question is if you're on Ubuntu 12.0, oh, if you're on Arch, this edition, are you using Debian? Oh, if it's Linux Mint, then those files are actually, no. There has to be like an answer to the question. How do I fix this problem? Here is the answer. That's it. It can't be 20,000 different web pages that each have a totally different answer, right? Completely unacceptable. You know what I'm saying? So off you go. Can you explain why you use F32 instead of double? Yes, F32s are twice as fast as doubles on current machines. The reason is because typically the clock cycle timing for an F32 instruction versus an F64 instruction is the same, but F32s can be done 4 wide, whereas doubles can only be done 2 wide. Or if you get up into future versions of the instruction set like AVX, then it's single position, F32 are 8 wide, and F64 are only 4 wide. So basically, if you can use F32s, you're twice as fast, pretty much, with your arithmetic ops, which is just always better. So unless you have a really good reason to use double, you generally don't want to, right? Or if you just don't care about performance, right? Then it doesn't matter which one you use. Use double for more precision, because you don't care what the performance is, problem solved. Is this something that could cause Stack Overflow or related to it? I don't know what this is, so I'm not sure. What you're talking about with unions, could they be related to the overflow of variables? If you did things wrong, I was asking because I was curious what error codes you could look for this problem. No, this has nothing to do with Stack Overflow. It doesn't really have anything to do with the stack at all. So I'm not sure I understand why you would think that was implicated. This has nothing to do with the stack. It's just how you interpret this space. So the space is the same regardless. It's always 128 bits or 16 bytes, right? It's always 16 bytes of space. The question is which kind of C type are you trying to say that it is, so that when you issue intrinsics, they're going to issue specific, you're going to be using one of these two types to issue a particular intrinsic. It's purely a compiler construct. It doesn't have any effect on the amount of stack space used because they both use the same amount of stack space. They're both the same size on the stack. So they can't really affect a stack overflow. Looks like we're good. All right, let's go ahead and close it down. All righty. Thank you everyone for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code so you can do your own experimentation with it. And for example, we're leaving on a cliffhanger this week. We need to analyze whether our code is whether we can generate good cosine-weighted distributions, and we only just started that. So you could play around with that this week and see what you think. And we need to do some mathematical analysis next week to see how we want to analyze these and whether we're doing a good job or not. So that's what we'll be doing next week, but you can beat me to it if you want. You've got all week to try it. And so that would be an interesting thing to play around with. And I'll be back here next week, same time, same place probably. Until then, have fun programming, everyone, and I'll see everyone on the internet. Take it easy, everybody.